In this exercise, we construct a truth table for these two propositional formulae involving the variables p and q. To do this, we'll write a column of truth values under each variable and operator in the formulae. So the first thing to do is to copy down the truth values of the variables wherever they appear in the formulae. So the p's all have the same columns and the q's all have the same truth values in their columns. Next, we need to look at the formulae and see which operators have highest precedence. So we are looking at the operators inside the brackets, inside the parentheses. So let's start with this OR operator. We can fill in the values based on the values of p and q. So first up, false or false is false. Next, false or true, that's true. Then true or false is true, and finally true or true is also true. We also have an OR operator in our second formula, which will have the same truth values. So we can fill them in. So since P or Q appears in both formulae, they'll have the same truth values, P or Q. Next, let's look at the AND operators. So we have P and Q. First up, false and false, that's false. Next, false and true, that's also false. And true and false is false again. And the last row, true and true, that's true. Again, we can copy these values for our AND operator in the second formula. The last operators to look at are the implies operators. And we need to make sure we're looking at the right columns here. We want P or Q implies P and Q. So we need to look at our OR column and our AND column. And this will give us our truth values for the implies. So first up, false implies false. And that's true. False implies anything is true. Next, we have true implies false. Well, that's false. Again, true implies false is false. And lastly, true implies true is true. And those are the truth values for our first formula. And again, for our second formula, we are looking at this AND column and this OR column. So we want P and Q implies P or Q. Now first up, false implies false. That's true. False implies true. That's true. And again, false implies true. Both of these are true. And finally, true implies true is true. And those are the truth values for our second formula. Now, what can we say about these two propositional formulae? Well, first of all, they are not logically equivalent since they have different truth values. And secondly, we can say that our second propositional formula is a tautology, since it's always true, no matter what the values of P and Q are. In this exercise, we construct truth tables for two propositional formulae involving the variables p, q, and r. Now, I've already jotted down every possible combination of truth values of the three variables. The next step is to copy these truth values down wherever the variables appear in the formulae. Now we can start to evaluate some of the logical operators. So let's look at the first formula, and we need to start inside the parentheses. So we have not q or r. Not is more tightly binding than or, so we start there. Not q. To get this, all we need to do is flip the truth values of q. And now we can move on to the OR operator. Now we're looking at the not column and the R column, right? We want not Q or R. So first up we have true or false. That's true. True or true is true. False or false, false. And then false or true is true. True or false is true. True or true is true. Then false or false is false. And false or true is true. Finally, we can evaluate this implies operator. Now we're looking at P implies not Q or R, and we need to look at the column we evaluated last, the OR column. So first up, false implies true. Well, false implies anything is true, so that's true. Likewise for rows 2, 3, and 4. Then we have true implies true, which is true, and we have that again, true implies true, so these two rows are both true. Then we have true implies false, which is false, followed by true implies true, which is true. And this column gives us the truth values of this formula. So the only time this formula is false is when P and Q are both true and R is false. Okay, now moving over to our second formula. Again, we'll start in the parentheses, and we have Q implies R. So that's easy enough to evaluate. False implies false, and false implies true are both true. Then true implies false is false. True implies true is true. False implies false, and false implies false. False implies true rather, are all true. True implies false is false. True implies true is true. Moving outside the parentheses, there are two more operators to evaluate, not and implies. Not is the more tightly binding operator, so we have to start with that. We have not P, which is simple enough. We just flip the truth values of P. And finally, we can evaluate the implies operator. And we want to look at the not column and this implies column. And that will give us not P implies Q implies R. So first up, true implies true, and again true implies true. These are true. Then true implies false, that's false. Then we have true implies true, which is true. And the remaining 4 rows are all false implies something, and that's always true. And there are the truth values of our second formula. We can see that the only time this formula is false is if P and R are both false and Q is true. And we're done. In this exercise, we construct truth tables for 2 propositional formulae involving the variables P, Q, and R. Now, I've already jotted down every possible combination of truth values of the 3 variables. The next step is to copy down the values of these variables wherever they appear in the formulae. So let's do that. And now we can start to evaluate some of the logical operators. So we need to first look inside the parentheses. So let's start with this implies. We have P implies Q. And first up, false implies false. That's true. False implies anything is true. So false implies false, and false implies true is also true. Now, true implies false, that's false. And the last 2 rows, true implies true, that's true. Now, we also have a P implies Q in our second formula, so this will have the same truth values. We can just copy those down. Okay, next let's look in these parentheses. Now, what do we need to evaluate first here? Well, the not operator is the most tightly binding here, so we need to evaluate that not first. So we have not P. All we need to do is flip the truth values of P. And we also have not P in the second formula, and we can do the same thing. Okay, now we can look at this implies. Not P implies R. Now the columns we need to look at here are the not column and the R column. And we are trying to say, does the first imply the second? Okay, so first up we have true implies false. That's false. True implies true is true. True implies false is false. And true implies true is true. And then for the next 4 rows, we have false implies something. Now, false implies something is always true, so the last 4 rows are all true. And we have the same formula here. Not P implies R, so this implies we'll have the same truth values. We can copy those down. Okay, we're on to the final operator of this formula, looking at the AND. Okay, now we need to be careful about which columns we're looking at here. We want this implies column and this implies column, the ones we evaluated last. Okay, and we're looking at this and this. So first up, true and false, that's false. True and true, that's true. True and false is false. True and true, true. Then we have false and true, false and true, both false. And the last two rows are true and true, true and true, both true. And this column gives us the truth values of this first formula. Let's move back to our second formula. Now we have an OR operator instead of the AND. We're looking at the two implies columns again. So first up we have true or false. That's true. True or true is true. True or false is true. True or true, true. False or true, false or true, they're both true. And then true or true, true or true, they're both true. So it's all true. Our second formula is true in every case. In other words, it's a tautology. And we're done. In this exercise, we're asked to construct the truth table for this formula. Now when we're filling in this table, we have to be very careful and use the brackets to help us determine in which order we can apply these logical operations. Right? Now the first step is to find all instances of our variables in this formula and copy in the truth values underneath. Let's do that. So now both of your A columns should match this A column, your B columns should match your B, and your C columns should match your C. Right, now let's think about which logical operator we can apply next. Well, we can do these two not operators, right? So the not column here will be the opposite truth value of the C column here, and the not column here will be the opposite truth value of the A column here. So let's fill in those. Now, let's apply this first implication. And remember, A implies B is false if and only if A is true and B is false. Right? And this implication is true in all other cases. So, looking at this, false implies false is true. And again. And then we have false implies true twice, both true. Now we have true implies false twice. And remember, in this case, this is false. And finally, we have true implies true twice, and both of these are true. Now we can do the same thing for this implication. B implies C, following the exact same rule. Let's fill this in. Now, consider this AND operator, right? So this statement says B implies C and not C. So this AND is true if and only if B implies C is true and not C is true. And so we're looking at the two orange columns, right? Let's fill this in. So you notice there are only two rows where both orange columns are true, right? And in these two rows, this AND column is true, and it is false everywhere else. Now let's look at this implication, right? Now we have everything in this bracket implies not A, right? So what we're looking at here is the two green columns. And following the same rule for implication as we have already used, right? We can fill in our implication here. You'll see there is just one row where the first green column is true and the second green column is false. So this is the only case where this implication will be false, right? Now finally we can turn to our last implication. Here we have this statement implies this statement, right? So what we're looking at here is the two red columns. Yes? And using the same rule for implication, we can fill this in. So here is our fully constructed truth table for this statement. And you'll notice that this statement is in fact a tautology. It's true in all cases. In this exercise, we will use truth tables to determine which of these 8 propositional formulae are logically equivalent to each other. Now, I've jotted down the truth values of P, and we can use these to fill in the rest of the table. So first of all, let's look at this column, not P. Well, for not P, we just flip the values of P. Next up, P implies not P. Okay, so first let's think about when P is false. Well, then we'll have false implies true, which is true. False implies anything is always true. If P is true, then we get true implies false, which is false. Next up, not P implies P. So first of all, if P is false, then we get true implies false, which is false. And if P is true, we get false implies true, which is true. Next up, P implies false. If P is false, then this is false implies false, which is true. If P is true, then this gives true implies false, which is false. Next, P implies true. Well, if P is false, then we get false implies true, which is true. If P is true, then this is true implies true, which is again true. In fact, anything implies true is always true. Next, false implies P. Well, if P is false, then we get false implies false, which is true. And if P is true, we get false implies true, which is again true. False implies anything is true. Finally, we have true implies P. If P is false, we get true implies false, which is false. And if P is true, we get true implies true, which is true. Okay, now looking at this table, we can see which of the formulae are logically equivalent to each other by seeing which have the same truth values. So we see that A, D, and H are logically equivalent to each other. B, C, and E are logically equivalent, and F and G are equivalent to each other. And we're done. In this exercise, we construct truth tables for 3 propositional formulae and use them to determine which of the 3 are logically equivalent to each other. So let's look at our first proposition. This is not P or Q. So first up, if P is false, then not P is true, and so not P or Q will be true. In our second row, Q is true, so not P or Q is true. In our third row, P is true, so not P is false, and Q is false, so we have false or false, giving us false. And in our last row, Q is true, and so not P or Q will be true. Okay, let's look at our second formula. This is not P or Q. So P or Q, that is true unless both P and Q are false, in which case it is false. So when we add the not, we just flip all of those truth values. So this is true when P and Q are both true, otherwise it's false. And our third formula, this is Q and P or not P. Okay, let's look at the first row. Well, in the first row we have P is false, so not P is true, and this formula is true. In the second row, again we have not P is true, and so this is true. In the third row, P is true, and so not P is false. So it all depends on whether this is true. Well, Q is false, and so Q and P is false. So we have false or false, which is false. And finally, in our last row, P and Q are both true. So Q and P is true, Q and P or not P is therefore true. So that's all of our truth values done. Now let's see which of these are logically equivalent. Well, the first and the third have the same truth values, so they are logically equivalent to each other, and the second is not. In this exercise, we construct truth tables for two propositional formulae and use them to determine whether the two formulae are logically equivalent. Now I've jotted down all the combinations of truth values of P and Q. So first, let's look at this sub-formula, P and Q. Now P and Q is false unless both P and Q are true, in which case it is true. So let's write down a column of truth values here. Next, let's look at this, not P and not Q. So this is true if both P and Q are false, right? If not P is true and not Q is true. Otherwise, this is false, right? If at least one of P and Q is true, then at least one of not P and not Q is false, and so this will be false. And we can look at the OR operator now. So we're looking at this column or this column. First up, false or true, that's true. False or false is false, and again we have false or false, both false. And lastly, true or false, that's true. And those are the truth values for our first formula. Let's turn our attention to the second formula. First up, let's look at P or not Q. So if P is true or Q is false, then this statement is true. So in the first row, Q is false. In the third row and the fourth row, P is true. In the second row, however, P is false and Q is true, and so this statement will be false. Now let's look at Q or not P. So this time, this is true if either Q is true or P is false. In the first row, P is false. In the second and fourth rows, Q is true. But in the third row, P is true and Q is false, and so this will be false. And now we can look at the AND operator. True and true, that's true. False and true is false, and true and false is false. And finally, true and true, that's true. And that gives us our truth values for the second formula. Now looking at the truth values for the two formulae, we see that they are the same in every case, and so they are logically equivalent. Again, let's start by formalizing these statements. We'll use the letter A to represent the statement Alice is telling the truth, and the letter B to represent the statement Bob is telling the truth. And so this first statement, either Alice or Bob is lying, can be translated to not A or not B. Our second statement, either Alice or Bob is telling the truth? Well, that simply says A or B. And finally, our conclusion is either Alice is lying or Bob is telling the truth. And so this says not A or B. Okay, now let's determine whether this is a logically valid argument. Remember, we need to check whether the two premises together imply the conclusion. And we'll again use a truth table. Let's first look at this or column. So not A or not B. This is true if either A or B is false, and false otherwise. So you see that the first three rows are true, and the last row, both A and B are true, so this is false. Now, this or column, this time this is true if either A or B is true, and false otherwise. So, in our first row, this is false, and in the second, third, and fourth rows, it's true. Now we can fill in this and column, right? This is just true if both blue columns are true and false otherwise. Okay, now let's look at this or column. So this is true if either A is false or B is true, right? So in the first row, A is false, and so this is true. In the second row, B is true, and so this is true. In the third row, A is true and B is false, so this is false. And then in our last row, B is true, and so this is true. Finally, we can fill in the implication. So, looking at the two green columns, false implies true is true. True implies true is true. True implies false is false. And false implies true is true. Now we can see that this is not a tautology, right? It is not true in every case. In particular, it is not true when A is true and B is false. That is, Alice is telling the truth and Bob is lying. And so this is not a logically valid. This time, we will use the letters BI to represent the statement the butler is innocent, the letters CI to represent the statement the cook is innocent, and the letters BL to represent the statement the butler is lying. So, our first premise says the butler and the cook are not both innocent. So, this can be translated to not BI or not CI, right? Either the butler is not innocent or the cook is not innocent. Our second statement says either the butler is lying or the cook is innocent. So, BL or CI. And our conclusion says the butler is either lying or guilty. So that's simply BL or not BI. Alright, and now to check whether this is a logically valid argument, again, we'll draw a truth table. And remember, if this statement is true in every case, that is, if our two premises always imply the conclusion, then this is a logically valid argument. Okay. So let's look at this or column here. So not BI or not CI. So this column is true if either BI or CI is false, and false otherwise. So you see that it is true in all rows except the fourth, where both are true, and the last. Now looking at this or column, BL or CI, so this is true if either BL or CI is true, and false if both are false. So this is false only in our first row and third row, and true everywhere else. Now looking at this AND column, so this is true if and only if both green columns are true, right? So let's fill this in. Now looking at our final OR column, BL or not BI. So this is true if either BL is true or BI is false, and false otherwise. So in our first row, BI is false, and so this is true. And again in our second row, BI is false. In our third row, BL is false and BI is true, and so this is false. And it is false again in the next row. In our fifth row, BL is true, and so this is true. And in fact, this is the case for all of the remaining rows. Now finally, we can fill in this implication column, right? And we're looking at the two blue columns now. False implies true is true. True implies true is true. False implies false is true. And again. True implies true in the next three rows. That's true. And finally, false implies true is true. So, having filled in the truth table, we see that this statement is a tautology. That is, the two premises do imply the conclusion in every case, and so this is a logically valid argument. In this exercise, we're given a deduction. Our task is to formalize each premise and the conclusion in this deduction, and then, by drawing an appropriate truth table, determine whether this deduction is valid. Now, the first thing we need to do is translate each statement into propositional logic. And to do that, we need some propositional variables. I've defined three. A stands for the statement, Alice will inherit the cottage. B stands for Bob will inherit the cottage. And C stands for Alice will inherit the houseboat. Let's look at our first premise. Alice and Bob won't both inherit the cottage. Another way to say this is, it is not the case that Alice and Bob will both inherit the cottage. So, not A and B. Secondly, Alice will either inherit the cottage or the houseboat. Or in other words, either Alice will inherit the cottage or Alice will inherit the houseboat. A or C. Our third statement is Bob will inherit the cottage. That's simple enough. That's just B. And finally, our conclusion is Alice will inherit the houseboat. So, C. Now we want to determine whether this is a valid deduction. Well, what does it mean for this to be a valid deduction? It means that if all the premises are true, then the conclusion must be true. In other words, the conjunction of the premises implies the conclusion. And if we draw a truth table for that statement and find that it is a tautology, then the argument is valid, otherwise it is invalid. So let's do that. Again, the statement we're looking at here is the conjunction of the three premises implies the conclusion. Now, if this is always true, that is, if this statement is a tautology, then the argument is valid. Otherwise, the argument is invalid. So let's start to evaluate this truth table. Now, the first thing I did was write down every combination of truth values of our three variables. Now, the next thing to do is to copy these values wherever the variables appear in the formula. Make sure that every A column is the same, every B column is the same, and every C column is the same. Now we can start to look at some of the logical operators. We need to start with the most tightly binding operators. So we're looking in the innermost parentheses. For example, we could start with this and. This and operator represents the statement A and B. So this is true if and only if A and B are both true. That is in the last two rows. Everywhere else it's false. Next, we can look at this OR column. This column is for the statement A or C. So this is false if A and C are both false, otherwise it's true. So in the first row it's false, and in the third row it's false, and everywhere else it's true. Okay, now staying on this side, this not operator is more tightly binding than this and, so that's what we'll evaluate next. This not column is for the statement not A and B. So to get this, we need to flip the truth values of A and B, which are given in the and column. We just flip all of those truth values. Right, now we have the values of not A and B and the values of A or C, and we can evaluate this and. This and column is for the statement not A and B and A or C. So this is true if the not column and the or column are both true, otherwise it's false. So looking at this, the second row is true, the fourth row, the fifth row, and the sixth row, and that's it. Now we can evaluate this and operator. This column represents this whole substatement, not A and B and A or C, and B. So this is true if both the and column here and this B column are true. If both of those are true, then this is true. Otherwise, it's false. So first row we have false and false, which is false. Then we have true and false, which is again false. Then false and true, which is false. Then true and true, so that's true. Then we have true and false, which is false. Followed by true and false, which is again false. And then the last two rows, false and true, and again false and true. These are both false. And we're almost there. The last thing to do is to evaluate our implication. So now we have a column, this and column, which represents the values of the conjunction of our three premises. And we're now checking, does this imply our conclusion? Okay, so first up, false implies false. Well, that's true. And in fact, false implies anything is true. False implies false, and false implies true are true. So we have false implies something, and false implies something. These are both true. Then we have true implies true, which is also true. And in the remaining 4 rows, we have false implies something. So false implies false, or false implies true. And these are all true. So now we have the truth values of our whole statement, and we can see that it is in fact a tautology, and so the argument is valid. In this exercise, we're given an argument. Our task is to formalize the argument, and by drawing an appropriate truth table, determine whether the argument is valid. And the first thing we need to do is to translate the statements of the argument into propositional logic. And to do this, we need some propositional variables. Now I've defined 3. S represents the statement sales will go up, E represents the statement expenses will go up, and H represents the statement the boss will be happy. Let's look at the premise of this argument. Either sales will go up and the boss will be happy, or expenses will go up and the boss won't be happy. Okay, now this is an either or statement, so it's something or something else. Either sales will go up and the boss will be happy, so that's S and H. Or expenses will go up and the boss won't be happy, so that's E and not H. And that's the premise of this argument. Now the conclusion is sales and expenses will not both go up. So another way to put this is it is not the case that sales and expenses will both go up. Not S and E. Now we want to determine whether this argument is valid. Well, what does it mean for an argument to be valid? Well, it means that if the premise is true, then the conclusion must be true. That is how you tell if an argument is valid. In other words, does the premise imply the conclusion? And that's what we'll draw a truth table for. We need the statement, the premise implies the conclusion. If we find that that is always true, then the argument is valid. Otherwise, the argument is invalid. Let's draw a truth table. Again, the statement we're looking at here is the premise of the argument implies the conclusion of the argument. If this formula is a tautology, that is, if it is always true, then the argument is valid, otherwise it is invalid. Now the first thing to do is to write out every combination of truth values of our 3 variables. So that's what I've done here. And next we can copy these truth values wherever the variables appear in the formula. You should make sure that all of your S columns are identical, all of your E columns are identical, and all of your H columns are identical. Now we can start to look at some of the operators. Let's start at the conclusion. Now we need to start inside the parentheses and look at this AND operator. This column will have the truth values of S and E. So this is true if S and E are both true, otherwise it's false. Looking at the values of S and E, we see that S and E is true in the last two rows, and everywhere else it's false. And staying in the conclusion, we can evaluate this NOT operator. This will have the values of not S and E. So to get these, all we need to do is flip the truth values of S and E. Okay, let's start to look at our premise now. Again, we need to start inside the parentheses. So we can start with this AND operator. This column is for the statement S and H. This is true if S and H are both true, which is in the last column and the third to last column. And everywhere else, this is false. Okay, and in our second set of parentheses, we have E and not H. The first operator we need to evaluate here is the not, since that's the most tightly binding. This is not H, so to get the values of this, we just flip the values of H. And now we can evaluate the AND operator. Again, this is true if E and not H are both true. So this is in the third row, true and true, and in the second to last row, true and true. Right? We're looking at the E column and the not column. Everywhere else, this is false. Now to finish off the premise, we can evaluate this OR operator. We're looking here for the values of S and H, or E and not H. Now, S and H is given by the AND column. E and not H is given by the AND column here. So we want the values of this column or this column. And this is false if both columns are false, otherwise it's true. And there are the truth values of our premise. Now the last thing to do is to fill in the implication column. Now we're looking for the values of the premise implies the conclusion. Now the truth values of the premise are given by our OR column that we just filled in. And the conclusion is not S and E. So the values of our conclusion are given in the not column. So we want to see, does this OR column imply the not column? Now first up we have false implies true, and this is true. Then again we have false implies true, true. Next, true implies true, which is true. Then false implies true, and again false implies true. These are both true. Next we have true implies true, which is true. And finally we have true implies false, which is false. And again, true implies false. Both of these are false. And the last two rows of this table show us that the argument is not valid. Even when the premise is true, sales and expenses can both go up. Exactly one of these things is true of my favorite number. Just based on that fact, can we determine what my favorite number is? Let's suppose that statement A is true, that my favorite number is 13. Well, in that case, my favorite number would certainly be greater than 7. So statement C would also be true. Since exactly one of the statements is true, this cannot be the case. So my favorite number is not 13. Similarly, if statement B is true, that my favorite number is 6, then the number would be greater than 5. So statement D would also be true. So again, this cannot be the case. My favorite number is not 6. Skipping to statement E, again, if this is true, if my favorite number is 10, then the number is certainly greater than 7 and greater than 5. So this is not an option either. Let's think about statement C next. Suppose this is true, that my favorite number is greater than 7. Well, then the number is also greater than 5. So again, we would have more than one true statement. So that's not an option. Which leaves only statement D. So this must be the statement that is true. My favorite number is greater than 5. Now we also know that my number is not greater than 7. It's greater than 5 but not greater than 7, which leaves 6 or 7 as options. But we also know that the number is not 6. So my favorite number must be 7. Which of these statements is true? Consider statement A. Is this true? All of the below. Well, suppose this statement is true. Then all the statements below are true, and in particular, statement E, none of the above, is true. But this is a contradiction, since then these statements would all be both true and not true. So statement A must be false. What about statement B? Well, suppose statement B is true. Statement B says none of the below. So in particular, statement C is not true. And statement D is not true. But statement D says one of the above. And in this case, one of the above is true. So statement D is true, which is a contradiction. So this tells us that, in fact, statement B must be false. Okay, what about statement C? This says all of the above. Well, we already know that none of the above are true. So statement C must be false. And statement D says one of the above, and we know that none of the above are true, so statement D is false. Now statement E says none of the above. None of the above are true, so statement E is true. And finally, statement F again says none of the above, but statement E is true, and so this is not true. And we're done. In this exercise, we're given a riddle, and we will see that by translating this riddle into propositional logic, we can apply precise logical reasoning to come to a solution. So, what is the riddle exactly? Well, we come across three boxes labeled A, B, and C, and the boxes have these statements written on them. So box A says there is no gold on this box, box B says there is no gold in this box, and box C says there is no gold in box B. Now, we are also given that exactly one of the three statements is true, and we want to determine whether or not there's gold in any of these boxes. Okay? So, the first thing I want to do is introduce some variables. So let A stand for box A contains gold, B stand for box B contains gold, and C stand for box C contains gold. Now that we have these variables, we can translate the three statements into propositional logic. So the first statement, there is no gold in this box, written on box A, tells us not A. The second statement, written on box B, says there is no gold in this box. In other words, not B. And finally, the statement on box C, there is no gold in box B. Well, again, that says not B. Now, remember, we're given that exactly one of these three statements is true. So, it can't be not B, because then two statements will be true. Right? So, the first statement, not A, must be true, while not B must be false. In other words, if not A is true, A must be false, and B must be true. A is false, and thus there is no gold in box A. Whereas B is true, so there is gold in box B. Now, there may or may not be gold in box C. We can't tell based on the three statements. we have found 3 boxes with a statement written on each. We know that at least one of these statements is true and at least one of these statements is false. What we want to know is, can we determine if there is gold in any of these boxes simply by reading the statements? Let's read the statements. Box A says there is gold in this box. Box B says there is no gold in this box. And box C says there is no gold in box B. Now I'm going to start by defining some propositional variables. A stands for the statement box A contains gold, B stands for box B contains gold, and C stands for box C contains gold. Now let's translate each of these statements into propositional logic. Box A says there is gold in this box. In other words, there is gold in box A. So that is represented by A. Box B says there is no gold in this box. In other words, there is no gold in box B. So that is represented by not B. B does not contain gold. And box C says there is no gold in box B. So again, not B. Now we know that at least one of these statements is true and at least one of these statements is false. So if A is true, then not B must be false. And if A is false, then not B must be true. So this means that A and B must either be both true or both false. That is, box A and B must either both contain gold or neither contain gold. But we have no way to determine which of these is true. Box C we have no information about. It may or may not contain gold. So it is in fact impossible for us to determine if any of the boxes contains gold. In this exercise, we're given a riddle to solve, and our task is to translate this riddle into propositional logic so that we can apply logical, precise reasoning in order to come to a solution. Okay, so what is the riddle exactly? Well, we come across 2 boxes labeled A and B, and we are told of these boxes that at least one of these boxes contains gold, and secondly, box A does not contain gold. Now, the final piece of information we are given is that either both of these 2 statements are true or they are both false. Okay? So let's start by defining some variables. Okay, so let's say that A stand for box A contains gold and B stand for box B contains gold. Okay, so now we can convert our 2 statements into propositional logic, right? So our first statement, at least one of these 2 boxes contains gold, well, that tells us A or B. Yeah. And our second statement, box A does not contain gold, that tells us not A. And the final piece of information we are given, that these statements are either both true or both false, well, that tells us that this statement is true if and only if this statement is true, right? In other words, this statement is true. Now we can build a truth table for this statement to see when it is true and when it is false. Okay, so let's do that. Okay, so let's start to build up our truth table. We'll first add the truth values of the variables in the table. We can now add the truth values for the OR operator on the left and the NOT operator on the right. And finally, we can add the truth values for the equivalence operator. Yeah, so let's do that. Remember, we're applying the operator to the two green columns. So we have false and true, gives us false. True, true gives us true. And then true, false, and true, false both give us false. So what this truth table tells us is that this statement, which we know is true, is only true in this one case, where A is false and B is true. In other words, we know that box A does not contain gold, while box B does contain gold. We need to determine which of the three children stole and ate the candy based on their statements. And we're assuming that the innocent children are telling the truth, while the guilty children are lying. Now Joel says that Felix ate it. And Joel is innocent if and only if what he says is true. So we can write this in formal propositional logic by writing J, if and only if, not F, right? Joel is innocent if and only if Felix is not innocent, right? Now Felix's statement is, if Joel had some, then so did Oscar. And Felix, again, is innocent if and only if his statement is true. And so we can write this. F, if and only if. And now we need to translate this statement. So if Joel had some, so if not J, then so did Oscar, then not O. And finally, Oscar just says, I didn't have any. So Oscar is innocent if and only if this statement is true. O, if and only if O. Right. Now we know that all three of these statements are true. So in order to determine which of the children ate the candy, we just need to find in which scenario, so for which truth values of J, F, and O, all three of these statements are true. And to do this, we can use a truth table to help. Right. Now you may have noticed that this third statement is actually a tautology, right? This will be true in every case, right? So this is why I've omitted this statement from our truth table. Really what we're checking is whether these two statements are both true, right? And if we find a case in which they are both true, then that must be the case we're looking for. Right. So let's start with this equivalence, right? This column will be true when J and F have different truth values, right? And it will be false otherwise. So let's fill that in. That's pretty straightforward. Now let's look at this implication. Not J implies not O. So looking at our first row, not F, so true, implies not F, so true. Does true imply true? Yeah, that's true. Okay. Does true imply false? No. That's false. Next, true implies true. Again, that's true. True implies false is again false. False implies true is true. False implies false is true. False implies true is true. And false implies false is true. Right, and now we can fill in this equivalence column, right? So this is true when F has the same truth value as this blue column, and it is false otherwise. Right, so let's fill that in. And now finally, we can fill in this AND column, right? And remember, when we find a scenario in which this is true, so that both of these statements are true, then that is the scenario we're looking for, right? So let's fill this in. First we have false and false is false. False and true gives false. True and true gives true. Next, true and false. True and false. True and false. Right? Those three are all false. And the last two rows, false and true are both false. And so there is exactly one case where all these three statements are true. In particular, this is the case when J is false, F is true, and O is false. So Joel and Oscar are guilty and ate the candy, while Felix is innocent and did not. Joel, Felix, and Oscar each write their name on a piece of paper, then exchange the paper so that no one is holding the piece with their own name written on it. We want to write a propositional formula that models this situation. In this formula, we are going to be using the exclusive OR operator. P XOR Q says that exactly one of P and Q is true. That is, either P is true or Q is true, and either P is false or Q is false. Now, there's a lot of information we need to include in our formula here. One thing we need to express is that the paper held by each boy has exactly one of the other's names on it. So for instance, on Joel's piece of paper is written either Felix or Oscar, but not both. FJ XOR OJ says that either Felix's name is written on Joel's paper or Oscar's name is written on Joel's paper, but not both. And we can write a similar statement for Felix's paper. Either Joel is written on Felix's paper or Oscar is written on Felix's paper, but not both. We know that both of these things must be true, so we can connect them with an AND operator. So FJ XOR OJ and JF XOR OF. And likewise for Oscar's paper, either Joel is written on Oscar's paper or Felix is written on Oscar's piece of paper. So that's quite a lot of information. This expresses that each boy has a piece of paper with exactly one of the other's names on it. But that's not all the information we have. Now let's call this formula P. And for a second formula Q, we want to express that each name is written on a piece of paper held by exactly one boy. So for instance, the name Joel is written either on Felix's piece of paper or Oscar's piece of paper, but not both. That is JF XOR JO. Likewise, Felix's name is written either on Joel's piece of paper or Oscar's piece of paper, but not both. FJ XOR FO. And the same goes for Oscar's name. Either Oscar is written on Joel's paper or Oscar is written on Felix's paper, but not both. Now, we have all the information we need. We know that both of these formulae are true. So for our final expression, we just need to say that P is true and Q is true. P and Q. Now suppose we look at Joel's piece of paper and it has the name Oscar written on it. That is, OJ is true. Can we deduce what name is written on each of the other pieces of paper? Well, looking through our formulae, since OJ is true, this means that FJ must be false, since exactly one of OJ and FJ is true. Now, since FJ is false, looking at our formula Q, exactly one of FJ and FO is true. FJ is false, so FO must be true. Now, since FO is true, and exactly one of JO and FO is true, this means that JO must be false. Now, since JO is false, and exactly one of JF and JO is true, JF must be true. So, from the fact that Oscar is written on Joel's piece of paper, we have deduced that Felix is written on Oscar's paper and Joel is written on Felix's paper.